we have Petar from ETH talk about matrix chaos inequalities and chaos of combinatorial type.
Take it away.
Oh, yeah. Thank you, March, for inviting me. And yeah, today I'm going to talk about this paper about random matrix theory, about very specific instances of them that are called matrix chaoses. This is a joint work with my advisor, Afonso Bandeira, who I think is also on this Zoom call. Kevin, who is also sitting in this room, he's another PhD student in our group, and Ramon van Handel, who is from Princeton. So yeah, as I said, it's going to be a very informal talk. I want to focus more on the proof technique, why it works, and please stop me whenever you want to ask any question. And yeah, I tried not to put too many slides, so it should be more of a discussion type. And March, how long should I go? Is it 50 minutes roughly?
Yes, 50 minutes.
50 minutes. Okay, I'll try to be on time. Okay, let's see. Okay, great. So just like a general introduction to random matrix theory, it is a very wide field. Now it's almost 100 years since Fisher's paper on random matrix theory. It appears in many different fields. There is a very important paper by von Neumann and Goldstein in numerical analysis, where they analyze matrix multiplication. Another work is by Wigner in 50s in nuclear physics, and actually the model that is present in this paper, I will now talk a bit about that model. This field is also intervened with number theory. There are even some connections to the Riemann's conjecture, and it's present in many other fields like theoretical computer science, combinatorics, machine learning, and so on. And maybe for the type of random matrices that I'm going to talk today, theoretical computer science is probably the one in which this type of random matrices appear the most. So about the Wigner matrix, so it's the fundamental random matrix model that is built in the following way. So we populate it with independent standard Gaussians, so ID N01, and let's force it to be symmetric. So we can do it just by populating the upper triangular part, and we get the lower triangular part by flipping. And since this model is present already for 70 years, there are many different things that are known about this model. One, the most important, is the semicircular law. So if you take this matrix, you normalize it by 1 over square root d, and I will talk later about why this normalization is appropriate. You take eigenvalues of this symmetric matrix, and you let d to go to infinity, and you can, for any d, you can plot a histogram of what these eigenvalues are, how they're distributed. If you let that d to go to infinity, this empirical spectral histogram will converge exactly to this histogram that is given by the semicircular distribution. Or actually, to be more precise, it's semi-ellipse, but let's just call it semicircular. And there are many other things that are known. It's not just that we know that there's convergence of the histograms. We also know that the top eigenvalue, that it goes to 2. So that it is not the case that we have arbitrarily large eigenvalues, but rather almost surely the top eigenvalue goes to 2. We even know what are the fluctuations, what's the distribution of the fluctuations of the largest eigenvalue around 2, and there are many other local laws known about this model. On the other side, in applications, it's not the case, it's not just the case that we work with Wiggins, but it's also that rarely it is the case that entries of random matrix model we work with are independent. They could be dependent in different ways. So while it is the case that entries are not independent, often it happens that the random matrix model that works in application is the one that has a linear structure. What I mean by that is we can express it as a sum of different random matrices. For example, one instance of linear structure is for Gaussian matrix series. So sums of independent Gaussians times deterministic matrices. Or we can look at something even more general, just a sum of independent D by D random matrices. Now, when this is the case, as it is with tossing coins, we do expect some concentration. And there are many different theorems known about when is, for example, norm of this random matrix, how much does it deviate from its expectation. And what I want to highlight here is, because there are many different theorems known about that, throughout the talk, we'll just focus on the expectation of the operator norm, because we can get tail bounds of the distribution of the operator norm from knowing what the expectation of the operator norm is. Second thing, which is quite remarkable, is that for many models, expectation of the operator norm can just be explained from matrix variance. So for now, we can just think of it as a generalization of the ordinary scalar variance, but there are some other things that are interesting about that. I'll talk about this later. But for now, this matrix variance parameter is the operator norm. Yeah.
Are all the AI symmetric matrix?
AIs are symmetric. I will mention this, but yeah, AI are symmetric matrices. When they're symmetric, the sigma parameter, the matrix variance, is given as the operator norm of the expectation of the matrix squared, and then square root taken outside. And what is remarkable about this parameter is that it's computable. But I don't mean computable in the sense, I mean, everything is computable. We should be able to get what numbers are. But what I mean by this is that it's given the model design, it is easy to get what these parameters are, precisely because now operator norm is outside of expectation. Before, the quantity that we want to understand, expectation of the operator norm, is much harder because we take expectation of some object that's hard to understand. Here we take operator norm outside of expectation. For example, if we take the Gaussian matrix series, because Gaussians are IID, have variance 1, we can just get that the sigma parameter is the operator norm of the sums of deterministic coefficient squares. In a general model, it will be sum of the expectation of the matrices squared. And this is really why it's all these concentration inequalities are working, because given the model, we can connect it to this matrix variance parameter. And this is a parameter for which, if you know how the model is built, it is not impossible to compute it. And throughout the talk, as March asked, I will make two standing assumptions. One of them is that we can just translate the random matrix, assume that it has mean 0. It's just a subtraction. So this is sort of without loss of generality assumption rather than just an assumption. Another thing is we can assume that the matrix is symmetric. So if we work with a matrix that's not symmetric, using this bigger matrix that's called Hermitian dilation of the original matrix, we can assume that we work with symmetric matrix because this bigger matrix has roughly the same spectral properties as the original one. So we'll just have these two assumptions for now, that it is a mean 0 matrix that is symmetric. And I'll now mention some classical random matrix inequalities that exist. One of them is the non-commutative kinship inequality by Luce, Picard, and Pizier. So this inequality says that if we work with Gaussian matrix series, we can upper bound its expectation of the operator norm by this matrix variance parameter, the sigma parameter, times square root log of the dimension of the matrix. So if it's a D by D random matrix, we get an additional square root log D factor. Maybe on the application side, a bit more familiar inequality is the matrix Bernstein inequality, which says that if you work with the general model, so just a model that is sum of different independent random matrices, and if you know that these random matrices are sort of not too big, so if their operator norms are almost surely bounded by this global constant R, then we get an upper bound very similar to the non-commutative kinship with an addition of a factor of this almost sure constant that almost surely bounds the summand times again a log D factor. So D is the dimension of the random matrix. And also we know that we can lower bound expectation of the operator norm by this matrix variance parameter. And I mean, here this remarkable should not mean that this inequality is remarkable, because this is just Jensen's inequality. But what is remarkable, that this inequality together with inequalities above say that matrix variance parameter in many cases is only log square root log D factor from the expectation of the operator norm. Now, if you compare this to the scalar case, so scalar case would be if D is 1, if you just have sums of scalar random variables, independent scalar random variables. And if you look at any textbook on concentration, what you would see is that there are standard techniques how to prove concentration results. For example, if you take the moment method, if you take the power of a sum of random variables and you analyze it, or if you take Laplace transform of your random variable, there are various ways in which you can bound it and obtain these concentration analogs of these concentration results for scalar random variables. And now, if you just want to generalize this for matrices, you would encounter an issue of the following type. Either you could not, because you're taking a power of a sum, you could not reorder summands that you get, or you could not factorize the exponential of the sum into single exponentials. And the reason why this happens is that it's just because matrices in general do not commute. If you have Zi and Zj, it's not equal to Zj and Zi, while it is equal for scalar random variables. Still, it is not hopeless. There are ways in which these scalar type arguments work by sort of having a relation like this to hold with some approximation. For example, for moment method, a common technique is called Buchholz's lemma, and for Laplace transform, a common technique is called Lipp's concavity theorem. And here I would point to a monograph by Joel Trop that explains this in a really nice way, why this works. But there is a way in which we can turn scalar concentration inequalities into matrix concentration inequalities by sort of going around this non-commutativity. But if you do this, we are not doing this for free, right? We have to pay something. And what we pay is this square root log D factor. And for a while, it was a big question, when is this square root log factor present? When is any factor, depending on the dimensionality of the random matrix, present? Why is it the case that these kind of inequalities work worse and worse as we expand them, as we increase the D factor? And maybe to give two contradicting examples of this phenomena, let's take the Wigner matrix. So it's the matrix I presented on the previous slide, and a Gaussian diagonal matrix. So it is another matrix that's populated with independent standard Gaussians, but we don't put D square of them, but we put D of them on the diagonal, and the rest of the matrix is 0. And let's compare how these two models behave. The left one, the Wigner matrix, we can compute. As I said, this matrix variance parameter, it is a computable parameter. What we need to do, we need to just sum these coefficient squares. So in the case of Wigner, these are Gaussians that appear throughout the matrix. AIs are coefficient matrices that say, oh, I use this entry here. So I can compute the matrix variance parameter of the Wigner matrix. And you would get square root D, which is precisely the square root D factor that I used to normalize the Wigner matrix to explain the semicircular law. And the expectation of the operator norm will roughly by Bai-in law be at 2 square root D. So the gap between the square root D of the matrix variance parameter and to the expectation of the operator norm is just a constant of 2. It doesn't get worse with D going to infinity. On the other case, if you take the diagonal matrix, which has D Gaussians, independent Gaussians on the diagonal and 0 on other entries, expectation of the operator norm is the maximum of diagonal entries because it's a diagonal matrix, but the maximum of D Gaussians roughly behaves as a square root log D factor, and matrix variance is just 1 in this case. So there is a gap of square root log D factor, which was precisely the gap that we saw between non-commutative kinship inequality and the lower bound that we get by Jensen. So this sort of feels like, okay, there should be this gap and there's nothing we can do about it, but that's not the case. And after a series of work, there was a big progress made by two of the people that are present on this talk. One is March, another one is Afonso, and the third person is Ramon, who is also working on this project, in which it was explained when is it the case that we're in the left scenario, which turns out to be the case for many different models. Well, we still don't know when is it the case that we're in the right scenario, but for many models, it was explained when it is the case that we're in the left scenario, that this gap does not exist. So the reason why this gap exists here is because we are taking maximum over entries. So we get this square root log D behavior. The reason why it doesn't exist on the left side is because these coefficients of where we put those Gaussians in a matrix, they in general do not commute. And it is possible to measure by how much they do not commute. And we can sort of capture when is it the case that paying this cost is unnecessary. It turns out that this is the case when these matrices behave freely. And the one way to measure when these matrices behave freely is through a so-called matrix covariance parameter. So this is an operator norm, again, a square root of an operator norm of a matrix, but here, this is a D square by D square matrix. So we have D by D random matrix, we have D square entries, and we form covariance matrix of these D square entries. The operator norm of the square root of the operator norm of this covariance matrix. If it is the case that this parameter is smaller than the matrix variance, we expect matrix to behave intrinsically free, which essentially means that the expectation of the operator norm is very close to the operator norm of the idealized version of the random matrix that we started with. And for this idealized version, we know that is only a constant for matrix variance. So again, this is an instance of a computable parameter, because given a random matrix model, we can compute the covariance matrix, operator norm is outside. And if it is the case, and often it is, that this parameter is smaller than the matrix variance, we can get sharp inequalities by not paying this dimensional factor. In another work by Ramon and Tatiana Brailovskaya, another phenomena that's usually referred as universality was observed, that if another parameter, this R parameter, the maximum of the summons, is smaller than matrix variance, and here smaller means much smaller in the polylogarithmic sense of D, then the total random matrix behaves as a Gaussian random matrix. Now, this is a very interesting statement because it says if summons are small, we behave Gaussian-like. But with inequality above, it says that because the inequality above is an inequality about Gaussian random matrices, about Gaussian matrix series. But with this universality principle, it says that if we have a general model, and it is the case that summons are small, we can relate it to a Gaussian-like model. And for the Gaussian-like model, we can check this condition of matrix covariance versus matrix variance. So what this means is that it's not just that we have sharpness for Gaussian models, but we can also get sharpness for non-Gaussian models when summons are small. And I will now stop talking general and I will start talking more particular about our work. So in this talk, we will work with models that are not linear. They don't have linear structure. They're not sum of independent random matrices. Rather, they have a polynomial structure. So now I'll put one scary definition what this polynomial structure is. So let's just look at the Gaussian case. So before we had sums of independent scalar Gaussians times deterministic D by D matrices, sum of GI, AI. Now, Gaussian metric chaos is a generalization of that in which we still have D by D matrix coefficients, but in front, we put all possible Q tuples of these M Gaussians. So this sum sort of has M choose Q. So M is the size of the dictionary that we have Gaussians to pick from. And we take all possible products of Q of them, products that have different labels, so that all terms in the process are independent scalar Gaussians times a matrix coefficient of that Q tuple. So it has Q chaos coordinates because there are Q, we call this chaos coordinates because there are Q different Gaussians that we have in the definition of this model. And there are two matrix coordinates because every coefficient is a matrix, so there are two coordinates. So essentially, this is sort of a Q plus 2 order structure. Now, this model is ubiquitous. It appears in many different applications, although in different fields, it is defined in a different language. Very often, it appears in the analysis of sum of squares algorithms in theoretical computer science. These models are usually not defined in this formula style way, but they're more defined in a graphical way. They're because they want to sort of what they want to analyze is this kind of chaoses that arise on complete graphs that have independent Gaussians on each edge, and then for some reason they form these chaoses upon that. That's the reason why these kind of models are described in a sketch-like way. So usually when they draw a graph like this in which they distinguish left and right side, so here we have 4 vertices, 2 on each side. They call this graph matrix, and given this shape, this Z-like shape, the way the matrix chaos is formed. So the 2 left vertices represent the tuples that enumerate rows. The 2 right vertices represent the tuple that enumerates the columns. Okay, so let's say if there are n of them in this sum, so we have an n squared by n squared deterministic matrices. This is the indicator saying that at this tuple row and this tuple column we put 1, so sort of like for a Wigner matrix. But at this place we don't put a single Gaussian, but we put the product of 3 Gaussians. Now, what are these 3 Gaussians? There are 3 Gaussians that are taken along these 3 edges, and we take a product of the IK Gaussian, the JK Gaussian, and the JL Gaussian. It is a very scary definition, but for a while there was a bottleneck how to analyze these chaoses, and this was really what initially solved this bottleneck. And then it appeared in many other applications. And another application in which it appears is in the analysis of Kronecker product random matrices in a recent paper. Also in the problem of ellipsoid fitting. I'll maybe go a bit quicker because there are so many of them. It also appears in the construction of quantum expanders. There is recent work 2 years ago now about how iterating Efronstein inequalities could help in the analysis of this kind of cases. It also appears in dispersive PDEs, which is very far from the other applications above. It also appeared in the differential privacy, compressed sensing, but maybe the two instances in which these structures appeared and which I want to highlight is first in the coupling inequalities. So Kvapian and Pena and Genet, they were analyzing when is it the case that these chaos-like structures that have couplings, right? Because here different chaos coordinates, they receive Gaussians from a second dictionary, so there is some kind of dependence that's hard to explain. When is it the case that if you make these coordinates independent, if you take different Gaussians for each coordinate, that this another object is sort of behaving the same as the original one? And another instance in which this appears in the operator space theory, and Hagerup and Pizier already more than 30 years ago found a way how to analyze this matrix chaoses. And this Pizier is the Pizier from non-commutative kinch inequality. So on the next slide, I will show how this is actually connected to the inequality I showed on the previous slide. One example that's maybe even more familiar than those 10 that I mentioned above is the Hansen-Wright inequality. So this is taken from a paper by Vershinin and Rudelson. So it is a statement about if you take n Gaussians and you form a quadratic, so you take sum of pairs of Gaussians times some scalar coefficients, how you can control this chaos. In this sense, these are tail bounds. And if you look at this definition, it is precisely what is written below. It's only the case that there are no matrix coefficients, but we only work with scalar coefficients. And this inequality says how this chaos, what's the tail bound of this chaos. If you look at the proof of this, they precisely use this principle of decoupling inequalities and of iterating linear concentration inequalities that originates from operator spaces. And now this principle of decoupling and iterating, I will show on the next slide how you can use it to bound Gaussian matrix chaos from this slide. So let's just look for Q2 for a quadratic case before it gets messy. So the object that we want to understand is the sums of pairs of Gaussians times d by d deterministic matrix. Before, we didn't have Gj. We just had sum of Gi, Ai. Now we have two of them. By decoupling theory, we know that up to a constant that only depends on Q, so Q is here too, so up to a constant, we can make these chaos coordinates independent. So instead of working with Gi, Gj, we can work with Gi, Hj, where H is another copy of M Gaussians independent from the Gs. So we can separate those chaos coordinates. Now, when they're separated, we can freeze one of them. Let's say we freeze the first one. We freeze G. So we just pretend it's numbers now that are not random. This becomes a linear random matrix. This has linear structure. Why? Well, if we take just sum over J, we have Gaussians, Hj's, times sum of I, Gi, Aij, which is now fixed. So it's a new coefficient, let's call it Bj. And we can use non-commutative kinship on that. So if you use non-commutative kinship, we upper bound it by some log factor. Let's not care about logs now, but what we care about is the matrix variance, right? So it is to upper bound expectation of the operator norm, we need to compute the matrix variance parameter of this linear random matrix sum of J, Hj, Bj. So it's given as the operator norm of the expectation of this thing squared. But if you would like to proceed from here, what would happen is that you started with the chaos of order 2, you used then non-commutative kinship, you removed one of the chaos coordinates, but then you need to compute a square of what you're left with. But then if you need to compute the square, you again need to compute something that's of order 2. So sort of, it doesn't feel that this is going to be iteration. It's just going to be, you go from 2, you decrease to 1, and again, you need to compute the square. So again, you're at 2. You need to understand chaoses of order 2. But what is interesting is that the matrix variance parameter is actually not a variance parameter. I mean, it is a variance parameter, but there is another way to think about this parameter that is to operators, that was to Pézières and to Hagerup and to operator space theorists more natural. So we can write operator norm of the expectation of something squared. Let's say these were scalars, for example. If these were scalars, right, what would be an expectation of a sum of scalars squared? Well, it would just be, so it's an L2 norm, it would just be the vector of those, the norm of the vector of those scalars squared. Now, for matrices, right, because expectation of y squared is sum of bj squared, you can check by linear algebra that this sum of bj squared, which is a d by d matrix, can be decomposed into a block matrix whose square is then equal to the expectation of y squared. As it is for scalars, it works for matrices. So we can compute the matrix variance parameter not as the sum of squares, but as the operator norm of the block matrix, whose blocks are the coefficients of the linear random matrix. And this is the identity which lets us do that. And if we do that, we are no longer working with chaos of order 2. We are working with the chaos of order 1 because the G's that we froze initially, if we just use distributivity, we can write this block matrix that after unfreezing is sums of GIs times the block matrix that has coefficients. But now, which coefficients do you pick? Well, you pick coefficients whose first coordinate I matches the Gaussian that was freezed, right? So you have sum of I, GI, and then this block matrix of these coefficients. So M of these coefficients. In total, you have M square of them. You have M block matrices of M coefficients. And you're tempted to use again NCK. So if you use NCK on G's, well, what would happen is sort of it won't work. The reason why it won't work is because even though we started with symmetric matrices, so these are D by D symmetric, we arrived to an M D by D matrix, which cannot be symmetric. There is no way this is symmetric. Actually, this is not the problem. The assumption that we had on random matrix being symmetric, it is more without loss of generality, and it's really not a restricting one. It turns out there is non-commutative kinship inequality for non-symmetric random matrices, and it is given by, it's not just the operator norm of one kind of block matrix that we formed, but it is maximum of two operator norms of two different kind of block matrices. One being the one in which you stack blocks one above another, and another one being one in which you stack blocks from left to right. Now, when these are symmetric, these two coincide, but when these are non-symmetric, these are different parameters. But you can prove a non-commutative kinship just by having matrix variance that the maximum of these two operator norms. And because you have this inequality, you have maximum, this sort of decomposes into two different problems. One problem being, let's understand linear random matrix that has these tall coefficients. Another one being, let's understand the random matrix that has these wide coefficients. These are non-symmetric coefficients, but we can use non-commutative kinship inequality for non-symmetric matrices. And if you use non-commutative kinship inequality on both of these matrices, what do we end up with? Well, for this one, we get two coefficients of this form. So these are huge block matrices. The first one, right, so we have these M squared D by D block matrix. So you can form even taller matrices. You can form M squared D by D matrix, just taking one after another, or you can take one by another, so you get an MD by MD matrix. For another, you get two kinds of them. You get one in which you put, so this was a D by MD, so it was like a floor. So you make a building out of this floor. You have MD by MD block matrix. Or you can get a very long one, D by M squared D block matrix. And now, after this procedure, starting with Gaussian chaos, decoupling it, and using non-commutative kinship inequality twice, we arrive to four different matrices that are deterministic, that are only given by the model design, and that are, again, as in the case of linear matrices, computable. It's calculable. We can, given a model, we can compute what these parameters are. And the iterated non-commutative kinship inequality for Q equal 2 would look like expectation of operator normal 1, y is upper bounded by, before we had square root log, now it's square root log squared. So there's a log factor times sigma of A, where this sigma of A is the matrix variance parameter of the chaos. So it is the maximum operator norm of four different flattenings. Flattenings are these different kind of deterministic matrices built of these coefficients. Right, before we had two of them, now we have four of them. But you can also iterate non-commutative kinship inequality to the lower bound, the Jensen-like bound. And before I said it is remarkable that really your square root log the
I want to say something. The A11 to AMM is not just the diagonal ones, right? It's M square of them. It's not just M of them, right?
It's M square of them. Here, yeah, it's M square of them. It's A11, A12, A13, then A21, A22. So it's all of them. It's not just
the diagonal.
No. So it's not the diagonal. So this is, yeah, this is much wider than this, and this is much taller than this. Right, so we have to, the block matrices that we end up with, they have all m squared blocks present. It's just the way in which we shape those blocks is different, right? And as I was saying, what is remarkable, right? I mean, this upper bound, it looks like terrible. I mean, we have to compute these norms of these huge matrices, but we could also iterate the lower bound on the non-commutative Kinchen in the same way. If we would just have to, instead of having this sign, having the sign in another direction. And we would end up with the same kind of bound without the log factor, but we would still end up with 4 different flattenings. Because non-commutative Kinchen is also true. The lower bound is also true with this matrix variance, which is the maximum of 2 flattenings. So it is really the case that the maximum of these 4 matrices up to a log factor is what determines expectation of the operator norm of this quadratic chaos. So this is really the correct measure. Although it is an intimidating one, it is the correct measure. And we can even do it for general Q. There's no need to do it for 2. For general Q, right, for linear we had 2 flattenings, for quadratic we had 4. You will get 2 to the Q different flattenings, and the maximum norm of these 2 to the Q flattenings would, up to a polylog factor, determine what the expectation of the operator norm of a general chaos is. So because we have these Q chaos coordinates, and in each iteration for each chaos coordinate upon which we use non-commutative Kinchen, we have 2 choices, whether we stack matrices like this or we stack matrices like this, we arrive to 2 to the Q flattenings. And these flattenings, as I said, these huge block matrices. Usually we would use this kind of notation. So R and C here represent different subsets of numbers from 1 to Q. And the RC flattening is a block matrix where sort of 4 chaos coordinates that you chose to stack coefficients like this, you enumerate this block matrix by this tuple of these R different numbers from 1 to m. For columns, you use C different numbers from 1 to Q. So it is a D to the M R times D to the MC matrix that has these M to the Q blocks arranged in different way, depending on which kind of bipartition of R and C of the set 1 to Q we have. And this was, I mean, what I presented now, this is not what we did. We sort of rediscovered this when we were doing it, but it was present for already 30 years. Klappian already had a decoupling inequality, this one that relates these two objects. And if you go look at the Alpenas and Ginés book, you can find this inequality there. If you go look at Pizier's book, you can find the work of Hagerup and Pizier that already had this idea of iterating non-commutative Kinchen inequality. So non-commutative Kinchen inequalities is late 80s. They already in the early 90s, they had a notion of how to iterate this non-commutative Kinchen inequality. They actually didn't think of it as variances. They thought of it as different flattenings, and they already had bounds like this, although not written in this language for these objects. But what for us was really interesting is that in most of these applications that I mentioned on the slide before, the way researchers would usually deal with these objects is by either devising a very complicated moment matrix method on the chaos itself and then solving it in a combinatorial way. Whereas it's very interesting that already 30 years ago, in operator space theory, people had notion how to deal with these objects. And then how, going from a chaos, you should only understand norms of these block matrices. And I will briefly later mention why understanding norms of these block matrices, although they're huge things, it is not that hard. But this really, the point of this slide is to say that already techniques were present. And this was sort of reinventing the fire. But the things that we add that are new is like we had for linear matrix concentration inequalities, we had these new inequalities that explain sharp-like and universal-like behavior. We observed that it is also possible to describe sharp-like and universal behavior for chaoses as well. So this is how it's going to work. Let us recall the notion of sharpness, right? For a Gaussian matrix series, so sums of independent Gaussians times deterministic coefficients, if the matrix covariance parameter was smaller than the matrix variance parameter, we knew that the expectation of the operator norm is close to its idealized version that is upper bounded just by the matrix variance without the dimensional factor. We can write this as an inequality, and this would be the powers. So it would be upper bounded by the matrix variance parameter as the main part, plus the error, which has some logarithmic factor, times the covariance parameter. And when this is smaller than this, we get up to a constant. We match the lower Jensen-like bound. I would maybe write this inequality in a bit different way, right? Because this was for symmetric matrices. Instead, you can write it as a sum of two matrix variance parameter, one describing the long block matrix, another one tall, another one describing the long block matrix. So we can rewrite it as this. I just separated the matrix variance parameter into two parts, whose maximum is the matrix variance parameter. Now, this covariance, so it's a operator norm of a d squared by d squared covariance matrix of the entries of the random matrix. We can write it in a different way. And it's actually like the matrix variance was really not a variance, but it was a flattening, a block matrix, a linear-like object. Also, the covariance is a linear-like object. So this object is a d squared by d squared matrix, but it is actually operator norm of d squared by m matrix squared, or square root here. So what is this matrix? So we had m different coefficients, and if each coefficient, if we vectorize that coefficient, instead of having a d by d matrix, we vectorize it into d squared by n vector, and we put one vector after another, we arrive to d squared by m matrix. The norm of that matrix is equal to the matrix covariance parameter. And like before, as I said, before we presented matrix variance parameter in a block matrix form, I said, okay, if we iterate in CK, starting with chaos of order 2, we would end up with chaos of order 1, whose parameter is a chaos of order 2. But precisely because this is a linear-like parameter, we can iterate this kind of inequality and end up with the chaos of order 1. And on this scale, on this linear random matrix that has these new coefficients from this part, we could again use this inequality. And we would end up with many different flattenings. For universality, a similar kind of phenomena occurs, right? The parameter for universality was that the summands are not big, right? The summands not big, this was the R parameter, which was the maximum operator norm of these summands. Here I'm just looking at scalar matrix series. So let's just look at sum of HI, AI, where HI are non-Gaussian-like random variables. So this is the maximum operator norm of these summands. Let's assume these are bounded random variables. So essentially it's the maximum operator norm of the coefficients themselves. This is how this inequality actually looks like, the universal inequality for this is actually the matrix Rosenthal inequality for a scalar-like random matrix. And again, a similar phenomenon occurs. The maximum summand parameter, the R parameter, which is the maximum operator norm of the summands, let's assume random variables are almost surely bounded by something that is in this constant. Maximum operator norm can be represented as the operator norm of the block matrix. Now, where on the diagonal, we put blocks of these coefficients, and on other blocks, we put zeros. And this is a linear-like parameter in the matrix coefficient data. So again, this inequality is iterable. Here's what the picture looks like. If you have a linear random matrix, like this, let's say sum of 3 Gaussians times their, okay, it can be even non-Gaussians times their deterministic coefficients. The sigma parameter, there are 2 matrices that we need to take care of. These are these 2 block matrices in which we stack blocks in different ways. The V parameter is the one in which we vectorize coefficients and put them one to another. And the R parameter is the one in which we diagonalize the block matrix. But really, all four parameters in all the inequalities I mentioned for linear random matrices, they're linear in the data. They're linear in this A1, A2, A3. They're just a map from matrix row to matrix row. And because of that, it's iterable, because in any step, we get rid of randomness. We get rid of random matrix coordinate, random coordinate. And because of that, starting with chaos for the Q, after Q iterations, we can arrive with 4 to the Q different flattenings, because at any step, we branch it to 4 different sub-chaoses for the Q minus 1. Actually, we arrive to maybe a bit less of 4 to the Q minus 4 to the Q of them, because we can arrive to the same one in different ways. But at least we know we arrive to exponentially many deterministic matrices that describe this kind of phenomena for matrix chaoses. We call them flattenings. So before, the formula I put for flattenings was the one in which we aligned blocks in different ways, because it was a sort of a tensor of order Q of D by D matrices. But essentially, there are, as I said before, there are Q plus 2 coordinates, right? There are Q coordinates that are chaos coordinates, and there are 2 coordinates that are matrix coordinates. And the total amount of numbers that we have here can be embedded in a Q plus 2 tensor. The tensor for the Q plus 2, right? Because we can also expand it to be together a tensor for the Q plus 2. And to this tensor, we form 4 to the Q plus 2 different flattenings. And these flattenings are very similar to the talk Ishak gave 2 or 3 weeks ago. So we form these different matrix flattenings. So for any subset of R and C, we decide which coordinates go to row side, which coordinates go to column side, and we populate it with these numbers. Turns out, as we iterate, sigma parameter will be given as the maximum of 2 to the Q operator norms of flattenings that preserve the matrix structure, right? Because we never collapsed the matrix coefficient themselves. So these are all kinds of flattenings in which the first matrix coordinate, the original row matrix coordinate, goes to row side, and the original column matrix coordinate goes on the column side. And for all Q chaos coordinates, we have 2 to the Q choices. The V parameter, the one parameter that comes out of iterating this inequality, will be another disjoint class of flattenings. But there is a way to have a bookkeeping device and to see which flattenings arrive in the error term. And the same can be for this Rosenthal-like for the diagonal parameter. So these up to 4 to the Q plus 2 flattenings, there is a way to separate them into disjoint families such that if the new V parameter is smaller than the sigma parameter, the matrix chaos behaves sharply, meaning that this matrix chaos variance parameter truly up to a constant describes the matrix chaos, like it did for the linear random matrix. And the same thing holds for universality. So this is how it is possible to transport these conclusions for linear random matrices to matrix chaoses. And I will just go quickly to maybe convince why computing, right? We have exponentially many huge deterministic matrices. Even though they are saying something, why it is even possible to use them to say something? Well, often it is the case that the matrix chaoses people work with, for example, the graph matrices, coefficients are often just deterministic 0-1 matrices. It's often just indicator matrices that at some entry in some combinatorial way have 1 and in the rest have zeros. And these family of matrix chaoses, we call them matrix chaoses of combinatorial type. And because blocks are deterministic 0-1 matrices, the flattenings that we need to analyze later are just huge matrices, but they only have zeros and ones. And to compute norms of these matrices, you sort of only need to count how many ones do you have per row and per column. And actually, counting, there is a way how to, for this general model that's called matrix chaos of combinatorial type, there is a way how to count this. So I will, because I'm short with time already, I will just briefly mention how it works, and then later you can ask me questions or by email. But for example, one notion of this matrix class of combinatorial type are so-called Counterparts matrices. So as I mentioned, they were used in differential privacy, but they're also used in numerical linear algebra. If you take two Wigners, let's say D by N, you should think N of being longer than E here. And you take counterparts product. So what is a counterparts product? It's a D square by N matrix in which you take first row of Wigner 1, first row of Wigner 2, and you take Kronecker product of two of them. You do for the second row, for the third, and so on. For this matrix, it admits this combinatorial structure because coefficients are just deterministic 0-1 matrices. And Rudolphson proved that its expectation of the operator norm is given as a maximum of these entries of D and N. What I want just to show you is that what happens is when you want to calculate flattenings of these huge block matrices, counting zeros and ones is one way to see it. But another way, what happens is that because these matrices have a combinatorial structure, the flattenings themselves, they decompose into tensor products of subflattenings. And understanding these subflattenings is much simpler. Essentially, what happens is these huge block matrices, once you delete redundant rows of zeros, rows and columns of zeros, they decompose into products of either identity matrix, all one column vector, and all one row vector. And computing these is just either square root norm or of the ambient dimension or one. So essentially, to compute these kind of parameters, you only need to take, right? You only need to track whether you go to row side or to column side, and then there is a way how to figure out how are these flattenings decomposed into tensor products. And this way is not just like a way that's for a very specific model. It is actually, if you write it in this form, you can even, there is an algorithm describing how you can count these flattenings, so you can get norms of these flattenings. And okay, maybe this picture doesn't mean a lot now, but what I want to show by this picture is that actually when we inputted Counterparts product into our program, where we just wrote a short script, it literally, by using this algorithm that is a combinatorial rule, it literally computed what are norms of all these exponential many flattenings. And it matched, of course, what Rudolphson proved for these matrices. So what I want to show here is more that there is an automated way to compute it, and it's even fully automated because you can put it on a computer. But even more interestingly is because this algorithm, it's just a set of rules how to compute these flattenings. You can even, for a general Q, right, because we need to understand exponentially many flattenings, you can even for a general Q solve it analytically. And this is how in our paper we solve it analytically. You can literally, for these exponential many of them, you can solve what is the maximum contribution you can get of these flattenings. And often it's the case that it's actually the proof is not that long. So what I want to convince by this screenshot is that actually you don't need the infinite computational power to get to arbitrarily high cases. And as a final slide, I would say that there was an assumption on the cases that we had that right, that the Q tuples that we take of Gaussians are all distinct. The reason why we had to take it because, right, we had right, the non-commutative Kinch inequality that we used was for mean zero random variables. But the problem is, right, if you take Q tuples in which sum of the random variables is repeated, let's say it's repeated twice, it's a square, and the random variable square has non-mean zero, is not mean zero. And because of that, you pick up different kind of behaviors. And what it turns out is that you actually pick up different kind of flattenings, and we are currently working out and figuring out which exactly flattenings do you pick, other than this 4 to the Q plus 2 that I mentioned. In this paper, in the paper that's about the chaos of combinatorial type, we show how still, like now, we can do it by hand, decomposing this general chaos into these square-free components. These are components that only receive different random variables in tuples, to which we can use this theory. So it is possible to separate it by hand into these sub-chaoses and then use the theory. But what we work on currently is how to generalize this. This is referred to a longer manuscript. There are some very natural questions that came during this work. The first one is this V, this covariance, matrix covariance parameter. It is a linear parameter, but what I mean here by linear, it is really a parameter about linear random matrices, right? This intrinsic freeness phenomena is a phenomenon about linear random matrices. And once you decouple and iterate, you can use this inequality, but you sort of don't capture the intrinsic freeness that the chaos itself generates. And this V parameter takes exponentially many different flattenings. It's still, for some examples, it didn't see that the chaos itself, even though we know it behaves freely, this parameter didn't capture that it behaves freely. And then there is a question, what would be a correct parameter? Like this parameter, which kind of flattenings would it need to include in order to obtain sharper inequalities for matrix classes? As I said, many of these matrix classes, they appear in sum of squares as in the analysis of sum square algorithms. One actual question is also which current lower bounds that we know could we improve with these new bounds. Also, we just work with the expectation of the operator norm. Now there are many results known. Now there are some results known about the whole spectrum. Could we generalize these results to get the spectrum of the matrix chaos itself, to get more information, not just about the top eigenvalue, but also about how this spectrum looks like? Thank you for your attention. And this is my email. I'll be happy to answer any questions. And I just want to advertise our group blog, Random Strasse 101. We write about different questions we do research on. Yeah, thank you.
Thanks a lot for a great talk. I will stop the recording here.